SwayamPrabha. Digital India. Educated India.
Okay, so we are going to continue our discussion in this lecture, load instability and tearing. In the last session, we discussed about the meaning of imperfection that you can give in the sheet, and then what is the use of that, and then we derived an equation for n minus epsilon u. Okay, it's a function of imperfection severity, that is dA naught and n, strain hardening exponent, right. So, we will continue our discussion in this session. So, next one what we are going to see is the effect of rate sensitivity or strain rate sensitivity. Okay, so we understand this particular topic. Rate sensitivity means how sensitive is our deformation with respect to change in strain rate. Slowly or quickly you do the test. So, how is going to affect the deformation, okay, or instability development or limit strains. Okay, so that is what the main aim here is. But until now, what we have assumed is basically the material actually strain hardens, okay, and mostly it's insensitive to strain rate. Mostly it is insensitive to strain rate. That's what we were assuming, but that can happen in room temperature. Okay, but the problem is, when necking starts, then the effect of strain rate is going to become significant during that process, during that localization or necking process. Even at room temperature, when you assume the strain rate effect to be small, okay, but if you see that once necking starts, then the effect of strain rate is going to be significant. So, we cannot actually neglect the effect of strain rate, okay, because when necking starts, we will see that in due course that there is going to be unstable increase in one of the strains, and you will see that that's going to be a reason for material failure. Okay, so now let us assume a material which is actually non-strain hardening, but it follows this particular strain rate flow stress model, flow stress relationship, sigma 1 is equal to B into epsilon 1 dot power m, where m is called as strain rate sensitivity index. So, we are not bringing in n here, strain hardening exponent n, okay, is not available in this equation, which is a general equation that we have seen before. Generally, we have seen that equation before, but right now we are using sigma is equal to B epsilon dot power m, that type of equation we are saying. And here you know that m is called strain rate sensitivity index. We know how to get this material property, okay, and here, so B is actually a fit constant like what we see as K in case of Holloman power law equation. So, here you will see that epsilon 1 dot is nothing but a true strain rate, which can be defined as d epsilon 1 divided by dt, okay, that means rate of change of your major strain, okay, that is defined by epsilon 1 dot is nothing but d epsilon 1 divided by dt, which is equal to dl by L divided by T, and dl by L is nothing but your cross-head velocity that you use for tensile test, and it is nothing but V by L, where V is nothing but your cross-head velocity and L is nothing but your instantaneous gauge length, okay, during tensile test. So, you can get true strain rate from these two values, okay. So, you can see that epsilon 1 dot depends on cross-head speed and the gauge length, instantaneous gauge length L. Why? Because it is a true strain rate. Okay, so now let us again go back to this particular diagram which we have discussed in the previous class. So, you have a sheet with imperfection at this particular position, let us say, okay, and it is getting deformed. So, it is a uniform region, it is imperfect region. So, now the load can be written as P is equal to sigma 1a, which is equal to sigma 1 plus a sigma 1 into a plus dA. Okay. So, this will give the relationship d sigma 1 by sigma 1 is equal to minus dA by a, and you will see that when you have this particular equation, you will see that the difference in stress in these two regions, that is d sigma 1, that is this d sigma 1 is proportional to the magnitude of imperfection, is proportional to the magnitude of imperfection defined by dA. So, larger the severity of imperfection, you will have a large difference in the sigma 1 values between the necked region, which is nothing but an imperfect region, and the neighboring region, which is nothing but a uniform region. Okay. So, now what we are going to do is, that is what I have discussed here, difference in stress for the two regions is proportional to the your magnitude of imperfection, which is nothing but dA. So, now as usual what I am going to do is, I am going to use this particular material law, and I am going to get a condition. So, now if I differentiate the material law, and if I differentiate the material law, I will get a condition for my this particular change in strain rate with respect to the strain rate, which is nothing but d epsilon 1 divided by epsilon 1 dot is equal to 1 by m d sigma 1 by m, sigma 1 by sigma 1 is equal to minus 1 by m dA by A. So, you have to differentiate this, and you can substitute here, you will get this particular equation d epsilon 1 dot divided by epsilon 1 dot is nothing but 1 by m d sigma 1 by sigma 1, and d sigma 1 sigma 1 is nothing but minus dA by A, and minus dA by A you can substitute here, you will get this particular relationship, and m is nothing but my strain rate sensitivity index. So, now this equation is going to tell you certain important observation. For a smaller value of m, you will see that the difference in strain rate, the difference in strain rate will be large and the imperfection will go rapidly. So, difference in strain rate means between these two regions, there is an imperfect region, there is a perfect region. Let us see, there is an imperfect region, and there is a perfect region. This is your neck, let us say, which is an imperfection we have, and this is a neighboring region, which is a uniform region. You will see that the difference in strain rate between these two, is proportional to m in this fashion. So, smaller value of m, which is generally seen in room temperature for most of the materials. At room temperature, if you evaluate m, it is going to be pretty small. You will see that there is going to be large difference in strain rate between this region and this region. If you measure it, there will be large difference in strain rate between this region, which is actually one important reason for imperfection to grow rapidly. So, this neck will be further localized, and you will have a fracture as quickly as possible if m is low, which is what you see in a room temperature type of deformation. But there are some materials like superplastic materials where m is going to be very large, of the order of, let us say, 0.3. You will see that the extension could be several 100% as the growth of imperfection is very gradual. So, for the neck to become severe, and you need to have a fracture in that particular, failure in that particular location due to localization of neck, you will see that m plays a larger role, and for those materials which has got pretty large m value, you will have several 100% of elongation or extension. Why? Because the neck growth is actually going to be very gradual. The imperfection growth is going to be very gradual, which is just opposite to what you have seen in this particular cases. For conventional material which are not superplastic in nature, you will see that it will grow rapidly. So, that is why these superplastic materials are generally having very high ductility of the order of, let us say, 100%, sometimes 300%. Why? Because it controls epsilon t minus epsilon u. So, epsilon t minus epsilon u is controlled by m. That is why we were saying that it is going to control the post-necking phenomenon, which is actually going to control the growth of neck, whether it is going to grow rapidly or slowly, gradually. So, some metals, people found out that like molten glass, which has got m of the order of 1, almost equal to 1, can deform almost indefinitely. So, in materials with lower m value, rate sensitivity will not greatly influence the maximum uniform strain, but it will affect post uniform elongation, in which materials with higher rate sensitivity will show higher post uniform elongation. So, necking will be affected by rate sensitivity. So, though maximum uniform elongation is not getting affected, but around that particular stage you will see necking is going to start, and that will be affected by rate sensitivity, and it is found that the post uniform elongation, we said that is epsilon t minus epsilon u, is higher in which materials having greater rate sensitivity. Okay. So, through this simple analysis one can study the effect of strain rate sensitivity index on the growth of neck. Okay. So, now the point here is as we said that in the neck region your strain rate is going to be very large as compared to the outside region. So, one can develop theories based on that to predict your limit strains or instability strains. So, now what we are going to discuss in this section is called as instability, tensile instability in stretching a continuous sheet. So, when we say continuous sheet, it means that for example, a conventional sheet which is undergoing deformation through tools like punch. Okay. So, generally sheets are deformed by punch, okay, which will give some geometric constraint on the development of strain distribution in the sheet. Okay. So, like punch can change the strain distribution and the contact can change the strain distribution because there is some geometric constraint given to the sheets. Okay. So, you will see that when we stretch a continuous sheet, the standard way we do it. Okay. So, you will see that a localized neck will develop in that location where diffuse neck was there before. Okay. So, like what we see in the case of tensile strip, and in that situations generally it is found that width of local neck. Okay. Suppose if you measure width of local neck is almost equal to that of your sheet thickness. Okay. And it is so localized that it generally does not affect the overall strain distribution outside that region. Okay. So, now what will happen because of such localization, okay, quick tearing can occur in that situations and your entire process will be over. The overall formability will be lost in that. So, if you want to analyze that, we as usual we take a sheet with undergoing deformation in this state of stress. You have sigma 1, sigma 2, sigma 3 is generally considered as 0 because of plane stress, and sigma 1 will give rise to T1, sigma 2 will give rise to T2. For a particular thickness, you can get these values, and that is what state of stress and strain is actually represented here for a proportional process. Okay. Of course, you have sigma 1 and sigma 2 is obtained by sigma 2 is equal to alpha into sigma 1, sigma 3 is 0. You have epsilon 1, epsilon 2 is beta into epsilon 1, and epsilon 3 will be equal to minus of 1 plus beta into epsilon 1, which you already derived. And principal traction can be obtained by T1 is equal to sigma 1 into T, and T2 is equal to sigma 2 into T, which is nothing but alpha into T1. These are all we already discussed, and one can get data from this. So, now what we are going to do is we are going to put a condition for local necking. We are going to put a condition for evaluate a condition for local necking, and as usual we are going to use maximum tension for that. So, we are saying that necking will to some extent start, okay, onset of necking, okay, is assumed to start when the major tension reaches a maximum value, which is represented by this particular equation. Okay. So, we are saying that dt1 by t1, and t1 is actually a function of sigma 1 and t. So, you can write d sigma 1 by sigma 1 plus dt by t, which is nothing but dt by t is nothing but d epsilon 3. D epsilon 3 is nothing but minus of 1 plus beta into d epsilon 1. With this entire equation can be framed. Now, what happens when the tension reach maximum? We are going to put this equation to be equal to 0. When we set it, we can get 1 by d epsilon 1 or d sigma 1 divided by d epsilon 1 into 1 by sigma 1 will be equal to 1 plus beta, isn't it? So, if you put this equation to be equal to 0, you will get this particular equation 1 by sigma 1 d sigma by d epsilon 1 is equal to 1 plus beta, and this equation is actually known to us before. Okay, in consider a condition we have also get this type of equation, and we in the left hand side we call it as a normalized strain hardening parameter. Okay, 1 by sigma 1 d sigma 1 by d epsilon 1 is equal to 1 plus beta. Okay, so here as usual your beta is nothing but your strain ratio. Okay, depending on beta values one can get this condition, and you will see that this equation is valid. It's very important. This equation is valid only for those processes in which beta is going to be greater than minus 1. Why? Because during this process we can expect thinning. So, this diagram you have to refer. Okay. So, beta is equal to minus 1 minus of 0 1. Okay. In all this process you will get some sort of thinning in the sheet while deforming. Only in those processes this equation is valid, and if you go in this direction, the one which is going to thicken, okay, below this, in this zone, if you pick up, okay, this equation is not valid. Why? For a simple reason that if it is a strain hardening material, the tension will never reach a maximum in this case. Tension will never reach a maximum, and we are putting a condition here, no maximum tension is reached. Okay, maximum major tension is reached. That is not going to happen in this type of situations where your beta is less than -1. Okay, why? Because it is going to thicken. On the other hand, if it is a strain hardening material, then further it's going to complicate the situation. The tension will never reach a maximum. So you cannot put this condition. This condition is valid in all these situations, okay, when you have beta greater than -1. Okay, the form of the equation is already known. Only thing is, in the previous equation we got, the previous model we got 1 by sigma 1 d sigma 1 is equal to 1. Okay, and then we applied sigma is equal to k epsilon 1 power n. We applied, isn't it? And then we got epsilon u is equal to n. Okay, if you remember that. Okay, but here the only change is it becomes a function of beta now. Okay, so now as usual we say that for a material obeying a power law like sigma bar is equal to k epsilon bar power n, and for 1 mesos material this can be written as okay, sigma 1 is equal to k epsilon 1 power n, and here I just mentioned k dash because k dash could be a function of k and alpha and beta. K could be a function of k, strain hardening strength coefficient, n strain hardening exponent, stress ratio and strain ratio. Okay, so if you want to use the original form of the equation, still one can use. Now what our problem is, now you have to, if you differentiate this particular equation and put a condition, you will see that 1 by sigma 1 d sigma 1 by d epsilon 1 will be equal to n by epsilon 1. N by epsilon 1. So it is going to be a similar derivation as we did before. Okay, only thing is like on the right hand side you have n by epsilon 1. So now both the left hand sides are equal, 1 by sigma 1 d sigma 1 d epsilon 1, and on the right hand side you have 1 plus beta, and here you have n by epsilon 1. So we are saying that 1 plus beta and n by epsilon 1. Okay, so n by epsilon 1 is equal to 1 plus beta. Okay, so since this is a process happening at instability when necking is start, so you can say epsilon 1 star as well. So epsilon 1 star is nothing but n by 1 plus beta, and epsilon 2 star is nothing but beta into epsilon 1 star, which is nothing but beta into n divided by 1 plus beta. Okay, so assuming that your beta is going to remain same even at maximum tension, or during necking. Okay, during local necking, during your local necking, isn't it? Okay, we are going to assume that beta is going to remain same, but then it may not be true. We will see that. Okay, so still you will see that you are going to have this particular equation. So epsilon 1 star will be equal to n by 1 plus beta, and epsilon 2 star will be equal to beta into n divided by 1 plus beta. Okay, so now if you add these two, okay, epsilon 1 star plus epsilon 2 star, you will see that it will be equal to n. It will be equal to n. So this is a simple condition for your local necking. With the help of maximum tension, we derived it. Okay, so with the help of maximum tension, we derived it. Okay, so now this epsilon 1 star and 2 star, as we discussed before, these are actually called as forming, okay, limit strains. These are actually called as a forming limit strain. One is major strain, other one is minor strain. Okay, so epsilon 1 star and 2 star are strains at maximum tension because it satisfies that maximum tension condition. Okay, and that equation can be drawn in this diagram. Okay, y axis being epsilon 1 and x axis you have epsilon 2, two principal strains, and if you plot that particular equation, epsilon 1 star plus 2 star is equal to n, it will give you a line like this, which is called as maximum tension line, and it will meet y axis at n. It will meet y axis at n. Why? Because epsilon 2, if you put 0 here, epsilon 1 will be n in that equation. So it will meet at n, and it is going to have an angle of 45 degree. Okay, so now, so what is the physical meaning of this line? This line tells that any data point you pick up, any epsilon 1 data you have it here, it's going to tell you that maximum tension is reached when you pick up that particular beta. When you pick up that particular beta, say for example, when you put, okay, beta is equal to minus half. Okay, when you put beta is equal to minus half in this equation, okay, beta is equal to minus half, let us say. Okay, here also beta is equal to minus half. If you put, what will happen here? So your epsilon 1 star will be 2n, epsilon 2 star will be minus n. Okay, so it is minus n comma 2n is a data point at which you are going to have localized necking if you follow beta is equal to your minus half, if you follow beta is equal to minus half. Okay, so that is the meaning of this particular line. Okay, similarly, if you follow any other beta value, you will get a different place at which you are going to have localized necking. Okay, and it also tells that as long as you are below the line, you are actually in the safe region. As long as you are below the line, you are actually in the safe region. Once you cross this line, that means maximum tension is reached. Okay, local necking is started, that means useful deformation formability is lost. So the material will be unsafe. Okay, above this. So I am writing failed region above the line. So this actual maximum tension line actually separates safe strains from failed strains. Okay, so below the line you will have useful forming window. So you can deform any sheet, you can make any component made of any material. Okay, so if you get this maximum tension line, you have to maintain the deformation such that all the strain data points will be below this particular maximum tension line. Then there is no problem. Okay, but there is one point here. So the important point here is when we do experiments, when we do actual trials, okay, and find out this epsilon 1 star and 2 star, there is some discrepancy as shown in this particular figure. So I think we understand the fact that like this kind of sheets can be used for different strain paths. We will discuss about it little later, and you will see that all these sheets will have circle grids on its surface of a particular dimension, and then you deform the sheet. Okay, say for example here all are deformed at different beta values. Okay, so here probably beta is equal to 1, to this could be beta is equal to 0 plane strain, to this could be beta is equal to your uniaxial value, whatever you have. Okay, so if you deform it and allow it to fail, okay, so the circle grids will be converted into ellipses. Okay, and you can measure your limit strains epsilon 1 and 2 closer to the neck region, and you can get epsilon 1 star and 2 star from this. Okay, from experiment's point of view, epsilon 1 star and 2 star you can get from this. Okay, so and you can compare that all this data, okay, with respect to maximum tension line as discussed here. Okay, so both the quadrants you can get for the first quadrant as well as second quadrant. So first quadrant, okay, and second quadrant, one quadrant is beta is greater than 0, the other case is beta is less than 0. Okay, so beta greater than 0, other one is beta less than 0. So this kind of data points can be compared from experiments as well as from maximum tension line, and that will lead to something called as forming limit diagram or forming limit curve. It's called forming limit curve, FLC. Okay, it will tell you the onset of local necking. Okay, which means as I told in the previous diagram, it will separate safe and failed strains in a sheet. Okay, but when you compare experimental data and maximum tension line, as I mentioned, okay, this is your maximum tension line and your experimental data is given, and maximum tension line is given, okay, and it continues here. Okay, both are shown here. Maximum tension line and experimental data are put in one graph and they are compared here. You will see that when you say beta is equal to less than 0, okay, that means minus half, 0, or in between, if you see the experimental data and maximum tension line to some extent coincide well. Okay, so when you go for beta is equal to less than 0, experimental FLC coincides with maximum tension line mostly, there is no issue. But on the right hand side, okay, in this particular stage, the right hand side beta greater than 0, if you see, there is significant difference between your experimental data and your maximum tension line. Okay, so your forming limit curve, okay, your forming limit curve from experiment does not coincide with maximum tension line that you get from the previous theory. Okay, why? Something is happening to the growth of neck, okay, which is not observed in other beta values until now. But if you pick up on the right hand side quadrant when beta greater than 0, okay, let us say beta is equal to 1. Okay, beta is equal to 1 would be forming limit curve would be somewhere here. If you take beta greater than 1 and if you take beta is equal to 1 for example, okay. So there is something, okay, that stabilizes the or slows down the growth of neck, okay, once tension reaches a maximum value, okay. So that stabilization actually delays whether your forming limit is reached or not, and there could be some more useful deformation, safe region, okay, that can be attained by the material. That is why you have large difference or some difference between your maximum tension line and experimental data, and the pattern is also different. You see the maximum tension line keep on decreasing, but on the right hand side you will see there is some increment in your forming limit strain, okay. So there is some process that delays or stabilizes or slows down the growth of neck, okay, once maximum tension is reached, okay. So what is that? Okay. So what is that? That can be understood from this particular analysis. So this diagram is already known to you. We already introduced this to you. So what we are considering here is a simple sheet, a thin sheet, okay, and you are seeing that the principal stresses sigma 1, sigma 2 are mapped here, and your 1 is along this one direction, 2 is along 2 direction, and it is undergoing deformation and a localized neck is formed here. Localized neck is nothing but this dotted region. This region is nothing but your localized neck. The cross section is shown here. You can see there is a local neck that is already formed here, okay. That region I am calling it as B, and outside region I am calling it as A, and that is also shown here, okay. This local region, localized neck region is called as B, and outside that region is called as A here, and it has got a thickness. Let us assume that the sheet has got a thickness, okay. We are going to define something called as a theta. Theta is actually the angle between the neck direction and the major principal stress, that is sigma 1, okay. So now there are certain things that we need to understand in this. First one is what we are saying is local neck as shown in this figure would occur along a line of pre-existing weakness at a limit strain, okay, in the uniform region that is approximately given by epsilon 1 star and 2 star, which is described before. Okay, what does that mean? That means that suppose you take a sheet and you assume that there is an imperfection like we have done before, okay, then necking is going to happen in the pre-existing weakness, let us say for example imperfection, okay, along that direction it is going to happen, and let us imagine that necking is going to happen in that location, then epsilon 1 star and 2 star, the uniform region is shown as a forming limit strain, okay. That is the physical meaning of this epsilon 1 star and 2 star, and how is it related to this B region is what is given here, okay. Local neck would occur along a line of pre-existing weakness at a limit strain in the uniform region, okay. Why? Because the defect is already weaker, it is going to fail first, okay. So we are going to have a conservative approach to choose epsilon 1 star and 2 star in the uniform region, that is in the A region, okay. So now if we identify the uniform region as A and imperfection as B, and imperfection meaning that is where necking is going to happen, then certain conditions have to be analyzed, assumed when we do this necking process analysis. What are the conditions? I have noted here. The stress and strain ratios we call alpha and beta must remain constant as assumed in the differentiation before, okay, before and during the necking process. Basically alpha and beta should remain throughout the course of deformation, okay, even during necking also, which is not actually true, but let us say it is like this. Then the process is a localized one. The necking process is a localized one. It is going to be there in a particular very small location, and the strain distribution outside the location is almost same. Something like that you have to maintain. And the neck must take a form of narrow trough. It is not, that is why it is called localized one, okay, narrow trough in the sheet rather than a patch or diffuse region that would influence the conditions away from the neck. So it is so localized that it should not affect anything happening outside that region, okay, which means that it is going to be a narrow trough, okay. So now what we are saying is once the necking process becomes severe, okay, so diffuse necking has happened and then now localization is severe, let us say, the uniform region A, this region A ceases to strain, okay, it will not strain, it will stop straining, okay, which means that the strain increment parallel to the neck in the y direction in the figure, okay, the strain increment parallel to the neck, that is along the y direction, okay, will be 0. So I am going to say that along the neck direction, that is y. Okay, I am going to say that d epsilon y is going to be 0. Okay. So, once the necking process becomes severe, the uniform region A ceases to strain, and moreover the strain increment parallel to neck. Okay, strain gradient will develop across the neck. Along the neck, it's going to be, strain increment is going to be 0. So, I am going to write d epsilon y is equal to 0. So, once localized necking is done, we can measure. There are a lot of grids on the seat surface. So, you can measure d epsilon y. Okay, practically you can measure it and see that. So, the increment is going to be 0. Okay. So, now let us go ahead to the next one. There is something called as geometric constraint. Okay, geometric constraint means these two regions are attached to each other, isn't it? So, these two regions A and B are actually attached to each other. Right. So, because of this geometric constraint requires that strain increment along the neck, must be equal to that in the same direction outside it. Okay. That means if you want to measure d epsilon along neck, that is y in B, that should be equal to the strain increment along the same direction in A also. Why? Because these two are actually constrained. These two are actually connected. That means the strain increment in y direction, both regions A and B along the neck must be 0. So, I am going to say that d epsilon y A and d epsilon y B, these two are equal and they become 0, which also in a way tells that my beta is equal to 0 for necking. Okay. So, beta is nothing but d epsilon 2 by 1. Okay, d epsilon 2 by 1. So, here you can say 2 is like, you can say y. Okay. So, which also tells a fact that your beta is equal to 0 for localized necking. This indicates that neck can develop only along the direction of 0 extension. 0 extension means what? That is along your y direction. With respect to this figure, it is along y direction only. In this particular region B, you are going to have development of neck. Okay. So, with this entire thing, from this figure, what we are going to do is we are going to relate. You can see that there are two coordinates x, y and 1, 2. We can relate these two. Okay. We can relate strain increments in these two axes, okay, 1, 2 and x, y by this equation. Okay. So, d epsilon y would be equal to d epsilon 1 cos square theta plus d epsilon 2 sin square theta, and this would be equal to 0. I am putting a condition now. So, by putting this condition, what I am going to do is I am going to show that when you take beta is equal to 1, that is when you pick up a beta value on the right hand side of this diagram, on the right hand side of this particular diagram, I am going to say that this direction of 0 extension does not exist. Okay. Whereas, if you put some other condition, for example, in this side tensile and plane strain, okay, the direction of 0 extension exists. That means there is some theta. There is some definite theta. This theta actually defines the angle, isn't it? So, the B region being your neck region, and the direction of that along y is going to define the direction of 0 extension. This theta is going to be something which we are going to calculate here. Okay. So, this equation relates your strains in 1, 2 with respect to your x, y, and I am using this, and this condition is already known to me, d epsilon y has to be 0. Okay. And now what I am going to do is for isotropic material, which is what we are discussing until now, under uniaxial tension, okay, this equation is already derived by us. D epsilon 2 is equal to d epsilon 3, that will be equal to minus d epsilon 1 by 2. We already derived this. Okay. So, if you put this condition in this equation, you will see that this equation will give you beta is equal to minus 1 by 2, and if you put it in this equation, it will give theta as about 55 degrees. Okay. So, you can get this. I mean, somehow you have to bring in beta into this. So, d epsilon 1 divided by d epsilon 1, here also d epsilon 2 divided by d epsilon 1 you can put. Okay. So, this will become beta. Okay. That beta value, if you put it here, you will get theta as about 54.74 degrees. Okay. So, then which means that there is some definite theta. Okay. That means the angle between your direction of 0 extension and the principal stress exists in uniaxial. Okay. Now, when you go for plane strain, we know that beta is equal to 0. So, if you put beta is equal to 0 here, okay, that means epsilon 2 by 1 is equal to epsilon 2 by epsilon 1 is equal to 0 here, then you will see that theta is going to be equal to 90 degree, which means the pre-existing that your 0 extension line is going to be perpendicular to sigma 1. There also it is existing. Now if you pick up one case on the right hand side, that is beta greater than 0, okay, let us say beta is equal to 1, I am picking up. If you put beta is equal to 1 here, so cos square theta plus 1 into sin square theta is equal to 0, it is not going to happen. Okay, that means here theta is actually does not exist, which means that there is no direction in which extension is 0 when you go for right hand side. For example, beta is equal to 1. There is no direction in which extension is 0. So just to conclude, if there is no direction of 0 extension, for example in the stretching process in which beta is greater than 0, we took an example of beta is equal to 1, the strains at which tension is a maximum are still given by epsilon 1 star and 2 star, but geometric constraints prevent the instantaneous growth of neck. Okay, so because of that reason, because of no direction of 0 extension, okay, for example when you have beta is equal to 1, okay, we say that so that actually delays the growth of neck or slows down the growth of neck, and hence there are chances that you will have larger strains in actual experimental data, okay, when compared to your maximum tension line. So that is why you have large difference in this particular zone, beta is greater than 0. Okay, so this can be explained with this particular simple analysis. Okay, so now let us go into the details of necking in the biaxial tension, how it is going to happen in the biaxial tension. So we pick up only one case, that is necking in biaxial tension, that is on the right hand side of your forming limit curve, that is this side, this side of the forming limit curve. Okay, so then we are going to this particular region and we are going to say how necking is going to happen. We are going to briefly discuss about it. As discussed before, in the first quadrant of strain diagram, your forming limit diagram, where both principal strains are positive, okay, so there is no direction of 0 extension. Okay, epsilon 1, epsilon 2, or let us say positive, okay, epsilon 1 will be always positive, but epsilon 2 could be positive or negative. So we are picking up this particular region where both are positive. There is no direction of 0 extension because theta does not exist. That is what we said. However, we say that under biaxial tension experiments, necking occurs actually. Okay, when you take beta is equal to 0 and deform, material is actually going to neck, but it happens at a strain level beyond the point of maximum tension. That is why you have larger epsilon 1 star and 2 star in the previous figure. Okay, so now what we are going to do is just to understand little bit more of what is happening in that region, we are going to use this particular schematic. This schematic tells about the biaxial stretching of sheet with imperfection uniform region. As usual, we are saying that so this sheet is actually stretched, okay, due to sigma 1 and sigma 2, two direction, one direction is defined, and as usual we are defining a region A and a region B. B is a region which is a weaker region which has got a thickness of TB when compared to A, TB is less. Okay, so here it is TA, here it is TB, TB is lesser than TA. Okay, and deformation is happening. Okay, and B region is a pre-existing defect, and that is where let us say that necking is going to start, and we are going to have a simplest case where it is going to be oriented perpendicular to the principal stress, that is sigma 1. Okay, B. Okay, so now the point here is this belongs to same material. A, B both belong to same material. Only thing is their thickness is different, which is nothing but an imperfection equivalent to all the imperfections in the material. Okay, so we are going to define something called as F. Okay, the imperfection is a groove denoted as B, where the thickness is TB. It is slightly less than the uniform region TA, and it is characterized by a factor F that is called as inhomogeneity factor, TB by TA. We are going to call F is equal to TB by TA. TB by TA is like, for example, TA, you take it as let us say 1 mm thick sheet, and TB would be let us say 0.9999 mm, very small heterogeneity you are picking up, inhomogeneity factor you are picking up. So 1 minus F naught, F is nothing but 0.001, you can say, something like that you can imagine. Okay, so I am putting F naught here for a simple reason that it is at the start of the deformation. It is at the start of the deformation, initial one, let us say, which means that there are chances that during course of deformation, during necking, this F can slightly change. Okay, so as discussed in the previous section, strain in the region B. Okay, strain in the region B. B is your this region, strain in the region B, parallel to the groove. would be constrained by the uniform region A, and I can say epsilon 2b would be equal to epsilon 2a, epsilon 2b. Okay, so that is 2. Okay, epsilon 2b, that is along this direction, these two regions are going to have same strain along two directions. Epsilon 2e, 2a is equal to epsilon 2b. Okay, so and the process is going to be a proportional process for the uniform region. Okay, so in the groove region, neck region, we don't know. So for the uniform region, we are saying that you are going to have sigma 1a, sigma 2a, which is nothing but alpha naught in sigma 1a. Again, I am using alpha naught, not alpha. Okay, because it's the initial one, let us say, on the uniform region, and sigma 3a is going to be 0, plane stress. Epsilon 1a will be there, 2a will be there, alpha naught will give you beta naught, and epsilon 3a is nothing but minus of 1 plus beta naught into epsilon 1a, which we already know. Okay, so now this T1 is nothing but sigma 1a Ta, which is nothing but sigma 1b in Tb, correct? It will be transmitted to both the regions A and B, and this will lead to this particular equation. We can say Tb by Ta, which is what we want. Tb by Ta would be equal to sigma 1a divided by sigma 1b, which is nothing but my F. Or you can say F naught also, nothing wrong in it. Definition remains same. Okay, so Tb by Ta is nothing but F, which is nothing but sigma 1a divided by sigma 1b. Okay, so you can see the relationship, okay, where Tb is generally smaller than Ta. So accordingly, sigma 1a and sigma 1b are related. Okay, so now deformation is happening with these constraints, and this is what will happen here. Okay, the same figure can be referred. So we are going to put one particular first stage, for example. So here is an yield locus is plotted, sigma 1 versus sigma 2, and red one is the initial yield locus, you can say. Okay, so now consider initial yielding. Okay, the entire material is going to yield. The material has got a definite yield strength, let us say sigma F naught. Okay, so now you are going to deform beyond uniaxial yield strength. Okay, what will happen is the groove region, that is this B region, will reach yield point first. Okay, why? Because your sigma 1b is greater than sigma 1a, correct? So your sigma 1b, okay, is greater than sigma 1a. Sigma 1b is greater than sigma 1a. So because it has to, it's a weaker region. Okay, sigma 1b is greater than sigma 1a for F less than 1, which is what we generally take, for F less than 1. So the groove will reach, or the imperfect region B will reach yield point first. Why? Because your sigma 1b will be greater than sigma 1a. So now the point is, the material in the groove cannot deform because of the geometric constraint epsilon 2b equal to epsilon 2a. Because of that, what will happen is, as the stress in A increases to reach the yield locus, okay, now A point will also start going in the same direction like that of B, and it will also reach your yield locus. By the time, what will happen? The point representing the region B must move around the yield locus to B naught. Okay, so you will see that when uniform region is deforming and reach yield locus, by that time what will happen is the B would slightly rotate and it will go to B naught. This itself indicates a fact that your alpha is not going to be same. Okay, it's going to be alpha naught is going to be changed to your alpha. Okay, so though we say it's a proportional process, here itself you will see that okay, the uniform region and the groove region are not going to have same alpha, it's going to be slightly different. Why? Because your sigma 1b is going to be larger than sigma 1a. Okay, so this is the situation. Now what will happen is, now what you are going to further deform the sheet. Considering some increment in deformation, okay, you are further deforming it, okay, for which increments parallel to the groove must be same, correct? So d epsilon 2a would be equal to d epsilon 2b, right, which is what we have seen before also. Okay, d epsilon 2a would be equal to d epsilon 2b, d epsilon 2a. Okay, so here, okay, these two should be, the increment should be same. Why? Because they are connected to each other. So this situation, what I am going to do, I am going to draw it in a vector diagram like this. So I am going to say that your d epsilon 2a and d epsilon 2b is represented by, okay, this length, and my sigma 1a is represented by this, and sigma 1b is represented by this. okay, and your A region is characterized by beta naught because of alpha naught, and your B region is characterized by beta corresponding to alpha. Okay, and you can see that your epsilon 1b is greater than epsilon 1a quite naturally. Why? Because your sigma 1b is greater than sigma 1a as per the previous discussion. Okay, your sigma 1b would be greater than sigma 1a, okay, and because of that, okay, your epsilon d epsilon 1b will be greater than d epsilon 1a, okay, and all the 4 strains can be vectors can be increment can be represented in this particular diagram. So, the strain increments across the groove will be greater than that in the uniform region, and inhomogeneity will become greater. So, F will also change during the course of deformation, okay, and as shown in the figure above, you will see that your d epsilon 1b is greater than d epsilon 1a. Okay, this can be directly interpreted from this relationship, sigma 1b is greater than sigma 1a, and that can be represented with this diagram, right. So, now what will happen is, so it is clear that in the B region, the strain in the groove, okay, or in the neck in the B region will increase ahead of that in the uniform region, but only slightly while the tension is increasing. Okay. So, you slowly deform the material, tension is increased, you will see that little bit ahead in B, strains will be little bit ahead in B. Why? Because your sigma 1b is going to be larger. Okay. But now this particular effect, the difference is going to gradually accelerate after the tension reaches a maximum. Okay. So, the growth of epsilon 1 in the uniform region and in the neck region or the groove region, okay, if that difference is going to accelerate, okay, when it will accelerate, and if it reaches a tension at a maximum and continues till the groove reaches a state of plane strain, beta is equal to 0, which is what is shown in this particular figure. So, it is the same figure, you will see that it is a plot between sigma 1 and sigma 2, okay, and this situation is already known to us, initial yield locus is there, and this point, okay, is for A, and it will slightly rotate for B, and because of that there will be some change in alpha, okay, with respect to alpha naught, okay, but if you further deform it and once tension crosses maximum tension, okay, what will happen here is you will reach a state of plane strain, which is what we have seen in the previous analysis also. Okay. So, like this, which we have seen in the previous one also, like for example beta is equal to 0, I said for necking will happen. So, here also you will see that slowly the beta value will tend to move towards this particular point where your alpha is going to be half, which is nothing but beta is equal to 0. Okay. So, it will reach a state of plane strain, which is shown in this particular figure. Okay. But in the case of A, it is not so. In the case of A, okay, this is for your A, no, A point, A location, it is not so like that. Okay. So, when plane strain is reached at BF, this particular F basically says that it is going to fail. Okay. B location is going to fail. Okay. The strain parallel to the groove ceases. The strain parallel to the groove ceases. The same thing has been represented in the strain diagram, epsilon 1 versus epsilon 2. You will see that. So, the strain parallel to the groove means your 2. Okay. Your 2, if you see, it is actually going to stop here. Okay. Like in the previous vector diagram, I am saying epsilon 2 A star, comma epsilon 2 B star. Epsilon 2 A star, this is epsilon 2 B star. Both are plotted here. You will see that in the A region, okay, it will go up to a particular extent, okay, up to this particular stage, okay, both B and A are going to remain same, almost same, but after some time you will see that there is an unstable increase in B. That's why you will see that it is going to suddenly increase when compared to A, but A keeps on straining, uniform region keeps on straining further here, and when epsilon 2A comma B reaches star, that means when it reaches your limit strain, you will see that these 2 points will also reach its star value, that is limit strain is actually reached. When plane strain is reached at BF, the strain parallel to the groove ceases because that is actually plane strain. Okay. So, along the groove it is going to be 0, but in the thickness direction and perpendicular groove there will be some gradient. Okay. The groove will then continue until failure or tearing, and the strain in the uniform region totally ceases. Okay. So you will have more strain localization only in the groove region, okay, to have a localized necking, and material is going to tear apart after that. If the localization is not there, it means that the strain is getting localized somewhere else also. Okay. Then you have to be a little bit careful that out of these two, whichever is weaker is going to dominate and material will fail here. Okay. So now you will, this particular diagram, you will see that your epsilon 2 star is going to be same. Okay. Why? Because it is along the groove region. 1A is going to be much smaller as compared to 1B. Okay. 1A is going to be smaller than 1B. Okay. So now this 1B, if you look at, and 1A if you see, this 1B strain is going to be several values larger than this. Okay. Maybe like 4 times, 10 times larger than with respect to A. Okay. So the strain state just outside the neck is of interest, so that epsilon 1 A star and 2 A star, when failure occurs, can be estimated and can be called as forming limit strain for a particular alpha naught and beta naught. Okay. So which means that this B region will undergo unstable increase in your in your epsilon 1. Okay. But you will see that this A region is not like that. It is going to be very uniform strain, and you will see that 2A and B is almost same. It is along the groove, and this particular diagram tells a fact that when localized necking happens, the reference is actually in the A region only. The reference is actually in the A region only, so that epsilon 1 A star comma epsilon 2 A star becomes a forming limit strain. Okay, becomes a forming limit strain. Okay. B region we do not choose because B region is already a necked zone. So just to have a conservative approach, you pick up a location just closer to the neck but in the uniform region and call that as a forming limit strains. Theoretically you can predict like this. So in the biaxial deformation, necking has got these many stages. Okay. So initially you will see that it is going to the groove region, or the B region is going to reach ill locus. By when A reaches, B will get rotated in this way. So B naught, A naught are represented. This itself tells that alpha is going to be different, and sigma 1B is greater than sigma 1A. Because sigma 1B is greater than sigma 1B, then d epsilon 1A is going to be greater than d epsilon 1B is greater than d epsilon 1A, which can also be represented in this strain plot, which tells that your strain increment in B is going to grow ahead of A. Okay. And once maximum tension is reached, around that particular situation you will see that in the B region the beta is going to actually switch or tend towards a plane strain type of deformation, and which means that plane strain means the strain along the neck region parallel to the groove or along the neck region ceases. Okay, which means you are going to put more strains in the other two directions. Okay. So you further deformate, the groove will or the neck region will further continue to deform, it will fail, it will tear, okay, and the strain in the uniform region actually ceases. Okay. But we always refer uniform region, okay, when this situation is happening, okay, and that will lead to epsilon 1 A star, epsilon 1 A star and epsilon 2 A star to show as forming limit strains. Okay. So now if you try to get strain rate in these two regions, okay, let us say in the A region and in the B region, if you compare strain rates, because strain is larger for a common time, you will see that strain rate in the B region is going to be several, it is going to be a multiplication factor, it is going to be large, much larger than the limit strains or the strain rates in the A region. Okay. Because strain is large for a common time, you will see that the strain rate also would be larger in the neck region as compared to A. Okay. So maybe like 4 times, 8 times, 10 times would be larger than in A. So this can be used as a measure for localized necking. Okay. So now let us assume that you are getting epsilon 1A and 2A stars, okay, which is going to denote a forming limit strain, okay, by following alpha naught and beta naught. Alpha naught and beta naught are the initial stress ratio and strain ratio that you have picked up and deform the sheet. Now you got forming limit strains now. Okay. So now you have to repeat the same strategy for various values of alphas and betas. Okay. So then you will get different data points in your forming limit curve. Okay, different data points mainly on the right hand side of forming limit curve, let us imagine. So you will get this first star, you will get the second star, you will get this third star. Okay, these 3 points, let us say epsilon 1 star and 2 star will give you, if you join it, it will give you a locus that will give you the forming limit curve on the right hand side. On the left hand side, we are still assuming that your maximum tension line is sufficient to get the forming limit. Okay, so on the left hand side is nothing but a maximum tension line, which you can get it from epsilon 1 star plus 2 star is equal to n. Combinedly, these two lines, this maximum tension line and on the right hand side, you repeat the same strategy for different values of alpha and beta and you get epsilon 1 star and 2 star and you plot together. This entire curve is called as a forming limit curve. In short, it is called as a FLC. Okay, so FLC is going to tell you when localized necking is actually going to start. So which also tells the fact that below this curve, you are actually in the safe zone. When you cross this, you are going to be a little bit careful. The material can fail or it's already failed. You have to be careful with this. So when as long as you are below this curve, you will be safe. Okay. Sometimes you can also define band for this. Okay. Band, this type of band can be defined, which means that there is a transit zone. Okay. So below this lower line, it is safe. Above this curve, it's definitely failure, but you are in the transit zone, okay, which tells the fact that you have to be careful the moment you enter into this particular zone. At any time, it may reach actual forming limit curve. Okay. So forming limit curve essentially is nothing but it's actually it's a locus of all the limit strains in different alphas and betas. Okay. And like your stress strain behavior, it's a material property. Okay. So you change something in the material, then it will change. Otherwise, it's not going to change. Okay. Say for example, you do some heat treatment, your forming limit can change. You do some material processing like friction stir welding, then your forming limit can change. Otherwise, it's not going to change. Okay. So what are the applications of forming limit curve? Okay. So failure diagnosis of your sheet grades. Okay. So when it can fail, what type of fracture. Okay. All those things you can understand from this. Quality of sheet estimation. So whether the material is a good quality with respect to forming limit or not. That's the main thing. Okay. So maybe material is good in terms of corrosion, but in terms of forming limit, whether it's good or not, we do not know. So that can be estimated. And you can select a particular sheet grade for a particular component. Okay. Suppose you want to make a sheet component used in let us say aerospace structures or automotive structures, okay, or even tube also. Okay. So you want to select, okay, then okay, it has to have a minimum forming limit to make that component. That's the meaning. What does that mean? That means if you make a component out of a particular material, let us say stainless steel, then in none of the locations in that component, it can cross the forming limit curve. The strains can cross the forming limit curve. It is not allowed. Okay. It means that suppose if you want to make a cup, a little bit a complex cup, which is used for some automotive application, okay, then you will have a big machine and then you have a die punch setup for that and you do it in shop floor, you can get that part and you can locally check, visually you can check, okay, whether there is any localized necking starts or there is severe thinning, okay, and if you measure epsilon 1 and 2 in that location by putting some circle grids, of course before deformation you have to put that and deform it and measure it in the location, then that will give you some idea of what is the value of epsilon 1 and 2 with respect to a forming limit curve of that particular material. Which means before going for component level, your stage, okay, you need to get forming limit of that particular stainless steel, for example. Okay, so that SS, let us say SS, stainless steel, some grade is there of particular thickness 2 mm. You need to have forming limit curve for that. Standard methods can be used, and you have to evaluate. And in none of the locations in that actual component, the strain can cross the forming limit curve. Okay, and you will see that in actual component. At any location you pick up, it's going to be one of the alphas or betas or in between. We have already seen 5 different alphas and betas right from the least in the second quadrant to your first quadrant, right. So in the sheet component you will see So, from this quadrant to this quadrant, you already you have seen that. So, now in the actual component you will see that it will follow one of this strain path or combination of all the strain paths. That is why this forming limit curve is going to be important. It tells actually the necking strains or the forming limit strains at various strain paths which a component can follow during the course of manufacturing. Okay, so in none of the locations it can cross this particular forming limit curve. So, which means the selection of material can be done for a particular component using this forming limit curve. Okay. Suppose this is a forming limit curve of one material and you make a component and you will see that at one particular critical location the strain has crossed this and it has reached here, this particular point, which means that the material is actually, component has already failed, okay, and you cannot make that component with that material. So, either you change the material or you change the process conditions. Okay, you are not it's not affordable for you to change the material, let us say, then you change the process conditions such that the same material you can make that component, which also tells the fact that selection of process conditions such as lubrication, forming temperature, strain rate can be decided based on this particular forming limit curve. Okay. So, now here I have made a note, the shape of forming limit curve depends on number of material properties and on the initial inhomogeneity factor, that is your F chosen theoretically. Okay. So, depends on, you have to assume an initial F to get a forming limit curve theoretically. So, it is said that your forming limit curve depends on F also. We will see that in due course how F is going to affect the forming limit curve, okay, by showing some schematics of forming limit curve, you will see that. Okay. So, we stop here and then we will discuss in the next session.